All right, so we're back here. So we'll do a few quick problems here to kind of illustrate some of the stuff from the last video, and we'll see how it goes. All right, so let's start with number 943 on page 422 in the 4th edition. So this is called Dr. Dog. Hey, Dr. Dog makes some pretty good music. I don't know, they're not bad. You should check them out. That's an actual band. But so it's saying in like whatever example it was, there's a p-value that was less than 0.001 for testing the null hypothesis that the probability of getting a dog's ability to diagnose bladder cancer in urine was a 1 in 7 chance. So first question, it's asking for the significance level of 0.05. What decision would you make? So what do you guys think? What do we do in this one? So since we have a p-value that's less than 0.001 and then alpha was previously set at 0.05, we would reject the null. Meaning dogs can smell cancer from urine. Okay, so pretty easy, straightforward, I would hope. So number B, or letter B, because it's not a number. We'll see this like chartreuse. If you made an error in part A, what type of error was it? Explain what the error means in the context of the dog experiment. So for this one, if we made one, this would be obviously a type. So that's the first part for sure. 1. So it'd be a false positive. So basically what we're saying is that we concluded dogs had this power. But they actually can't. So that's what we mean in that context, and that's how it would break even or break out. So let's do a new one. We get a new color again. We'll go back here. We'll do 9.45, fracking. Fracking errors. And we're picking this one because Texas had a big thing with fracking when I lived there. And it was kind of frustrating because all these earthquakes kept popping up and they're like, it's not due to the fracking, but it like kind of was due to the fracking because it was an area that didn't have any earthquakes, period. And then fracking happened and then earthquakes happened like all the time. Many ones, but like noticeable. So in here, right, we have the null hypothesis testing for fracking. So saying it's p equals 0.5 against the alternative hypothesis that the probability is less than 0.5. And so those opposing increasing fracking are in the minority. In other words, an example, what would be a type 1 error and a type 2 error? So that example was talking about like opposing fracking in the minority. So if we think about how this problem is, so if we go back and look at it, right? So a type 1 error. So a false positive. Would be that we would guess fracking opposition is in the minority. When they aren't. Are not. Part B, a type 2, a false negative, so we would determine that the null was correct. And there is no evidence of a minority who oppose fracking. When they are, in fact, the minority. Okay, so I think we're probably feeling pretty good about these kinds of examples. Seeing if there's like any other ones that maybe we kind of want to do. We kind of talked about this. Oh, yeah, okay, all right. So we'll do another one. So since we kind of looped this stuff together or combined them together, we'll do a new section since we talked about issues of practical significance. So let's look at problem 9.54 on page 429 in the 4th edition. So this question saying there's a study considers whether the mean score on a college entrance exam for students in 2010 is any different from those who had it from the mean score of 500 students took the exam in 1985. So it says we're gonna let mu represent the mean score for all students who took the exam in 2010. And for all students exam in 2010, for a random sample of 25,000 students who took the exam in 2010. So this is 500, and then this is the sample in 2010. This equals 498. And we have a standard deviation of 100. So the first thing it wants is show that test statistic is 3.16. So for this one, recall that the formula is x bar minus the null hypothesis average divided by the standard error, which is the square root, which is the standard deviation divided by the square root of n. And so this would be 498 minus 500 divided by 100 divided by the square root of 25,000. And this equals negative 3.16. So part B then is asking, so the p-value, what does it say? Find the p-value for testing that the null hypothesis, the mean, population mean equals 500 against the alternative that the mean does not equal 500. So what would we do this here, right? So basically, if we go ahead and look this up, this is two-sided. The z-score is less than negative 3.16. And this p-value would be 0.0016. So explain why the test result is statistically significant but not practically significant. So from a statistical standpoint, right? So we have what? We know that we have a large sample. We have a narrow margin of error. We know that there is there is a numeric difference between 498 and 500, but the difference, I'll put a triangle of 2, isn't a big deal. No one's going to lose any sleep over that. You know, are we really going to say that even though the students in 1985 had a score of 500 and students in 2010 had, 498, are we really going to say that they are substantively different from one another? No, we would not make that conclusion. Anyone who did, well, they just don't understand the difference between that. So that's why we have these kinds of questions. We also have, we'll throw in 9.55 on page 429. And so, like, looking at political conservatism and liberalism in the United States, suppose the sample mean, x bar equals 4.09, and the sample standard deviation is equal to 1.43, and the sample size, n, is 25. So how would we figure this out? So if we look back into like what that problem was saying, like back in there, it was saying that political conservatism was a 4, right? So we know that this is equal to 4 if we go back and look at that problem. So for part A, if we compute that t-score, again, which is equal to x bar minus the null hypothesis mean divided by s, or the square root of n. This is equal to 4.09 minus 4 divided by 1.43 divided by the square root of 25. And this would equal 0.31. So part B is asking what is the p-value for testing that the null mean equals 4 against the alternative that this, the null mean does not equal 4. And so if we go back and we go and look this up, right, we would see that the p-value is equal to about 0.76. We cannot reject a null. That the political ideology is equal to 4. So it's plausible it is correct. We don't, we cannot reject it. We don't necessarily accept it. Remember, we have kind of like talked about this a little bit before. So if we do part C and we start pulling in a confidence interval, remember, right, so we're looking at 4.09. And if we look at, since we're using this n of 25, if we go and look up the error for like 1.96, so if we look at the t-distribution for this, it'd be plus or minus 2.0639. Again, this is a small sample. If we go and look in the back of the book and find the appropriate degrees of freedom, in this case 24, we have a t-value of 0.025. You can find this information if we multiply it by the standard error, which is this number right here. Basically, we would find that it ranges from 3.5 to 4.7. So D is asking us, together with the results of example 10, explain what this illustrates about the effective sample size of the p-value for a given mean standard deviation and the width of the confidence interval. So in the previous example, there's like over 2,400 people, right? So what this ends up is that the p-value increases a lot. So a large sample finding may not apply to a small sample. The other thing to consider, what does this do with the confidence interval? The confidence interval becomes wider with a smaller n, smaller sample size. So hopefully that kind of makes sense for you. I hope this was useful, and I guess I'll see y'all later. So toodaloo.